Hey everyone, welcome to this explainer. You know, we all interact with the internet every single day, right? But just beneath the surface of your browser is an invisible symphony of technology, moving literally at the speed of light. Today, we are going to completely demystify the hidden architecture of the web. So let's think about this. What actually happens when you type a URL and press enter? It's the most relatable everyday action. You type stanford.edu or twitter.com, hit enter, and boom, a website is there. But that one tiny keystroke kicks off this absolutely massive amount of invisible complexity. A whole relay race of communication has to happen flawlessly before even a single pixel loads on your screen. Here's our roadmap for today. First, we'll look at the hidden internet journey. Then, DNS, the web's phone book. After that, the very real threat of DNS hijacking. Then, we'll cover the HTTP protocol. And finally, we'll wrap up by decoding the fine print. All right, part one, the hidden internet journey, milliseconds of magic. Moving into part two, DNS, the web's phone book, finding the right address. Okay, so here's the deal. Computers, they really don't understand names like stanford.edu. They only speak in numbers, specifically IP addresses. So literally, the millisecond you hit enter, your computer reaches out to a middleman called the DNS recursive resolver to look up stanford.edu. But the resolver doesn't know the answer either, so it has to query the absolute top of the internet's hierarchy, the root name server. The query flies out to the root. Now, think of the root as the grand central station of the internet. It doesn't actually have the final answer, but it knows exactly who to ask next. So the root name server fires back immediately, basically saying, hey, I don't know the exact IP for stanford.edu, but here's the address for the top-level domain name server that handles all the .edu websites. Armed with that new clue, our resolver bounces back and fires off a brand new query. This time, it goes straight to that .edu name server. We're getting much closer now. The top-level domain name server answers back. It tells the resolver, look, I don't have the final web page, but I know exactly who is in charge of Stanford specifically. And it hands over the address for the authoritative domain name server that exclusively handles stanford.edu. Finally, our tireless resolver asks that specific domain server. And because this server is the ultimate authority for this domain, it replies with the big prize, the actual numerical server IP address we've been looking for. In the very last step, the resolver hands this numerical IP address, in this case, 171.67.215.200, right back to your browser. Your computer finally knows exactly where to connect. And what's absolutely mind-blowing here, this massive global search, bouncing between multiple servers around the world, all happens in just milliseconds. It's crazy. So just to cement that whole process, it's 5 distinct steps. 1, your client asks the resolver. 2, the resolver queries the root. 3, it's directed to the top-level domain. 4, it queries the specific domain. And 5, the authoritative IP is returned. 5 steps every single time you hit enter. All right, part 3, the threat of DNS hijacking, the invisible interceptor. Of course, wherever there's a crucial system on the web, there are attackers actively trying to break it. So what if that trusted middleman, the DNS resolver, is compromised? Well, in a DNS hijacking attack, the attacker changes those target DNS records. So when your client asks for the IP address of, say, your bank, the hijacked resolver intercepts that query and silently directs you to a malicious IP address instead of the real server. You typed the right name, but the phone book gave you a fake number. And the worst part? Your browser has absolutely no idea it's talking to an imposter server. So why do attackers even do this? Well, the primary goal is usually phishing. They want to steal your passwords and credentials by throwing up a fake login screen that looks identical to the real one. But there's a huge financial angle too. By hijacking your traffic, they can force you to view unauthorized ads, or even worse, they can actually hijack your computer's processing power for covert cryptocurrency mining completely behind your back. It's a really silent and frankly incredibly dangerous threat. Moving on to part 4, HTTP, the conversation protocol, speaking the same language. Okay, so assuming we haven't been hijacked and we safely have the right IP address, the client and the server actually need to talk to each other. They do this using HTTP. But here's a totally counterintuitive fundamental about it. HTTP is entirely stateless. That means every single request is an independent blank slate. The protocol itself has zero memory of previous interactions. None. 2 requests have absolutely no relation to each other.
Now, you might be thinking, wait a minute, websites remember me all the time. I stay logged into my accounts. And you're right. But that memory, that state, is actually implemented as an extra layer on top of HTTP. It's not built into the HTTP protocol itself.
Now, when they talk, the server always replies with an HTTP status code. You can kind of think of these as the moods of the conversation. If you go to 100 level code, the server's basically saying, hold on, I'm processing. The 200 family, like the famous 200 OK, means here you go, total success. The 300 family is redirection, like go away, this moved. The 400s, including the infamous 404 not found that we all know and hate, that means you messed up, client. And the 500s? Well, that's the server panicking and admitting, okay, I messed up, this is entirely my fault.
Finally, Part 5. Decoding the fine print. HTTP headers.
Because HTTP is inherently stateless and pretty simple, it really needs a way to pass complex context and instructions, and it does this through headers. Think of these as the fine print attached to your request. For example, if we use a command line tool to manually send a request to a website, we can just add one single header like accept language ES. By doing that, we're explicitly telling the server, hey, I only want to understand Spanish. And just by tweaking that one little line of text, the server completely changes its response, delivering content tailored perfectly to that demand. Headers are literally how we pass cookies to stay logged in, how we tell the server what browser we're using, and how we negotiate data compression. They basically turn a very simple protocol into this incredibly extensible, powerful tool. So let's step back for a second and just think about what we've uncovered today. From the crazy multi-step relay race of DNS just to find a single IP address, to the stateless conversations dictated by HTTP headers and status codes, billions of times a second, all across the globe, this invisible complex dance happens flawlessly. Just so you can load a single web page. It's honestly a staggering achievement of engineering, but it also leaves us with kind of a provocative thought. Given how incredibly reliant we are on this hidden infrastructure, what would actually happen to our connected world if the DNS phone book simply went blank tomorrow? Just a little something to ponder the next time you press enter. Thanks so much for joining me on this explainer, and keep learning.